So we'll continue with our discussion of the Markowitz model in next week's lectures. But for now, let us do a few practice problems to make sure that we are comfortable with working with these concepts. So our first question involves basic portfolio construction, how to think about the expected return and standard deviation of the portfolio given individual information about the individual assets. So we have got two stocks, X and Y, with the following expected returns and standard deviations. So stock X has a expected return of 20% and a standard deviation of 20%, and stock Y has an expected return of 15% and a standard deviation of 25%. We are also told that the correlation between the return on X and Y is 0.2. So the first question is that if we observe these two stocks, we can clearly see that X has a higher expected return compared to Y, and X has a lower standard deviation compared to Y. So in that case, would any risk-averse investor ever want to invest in stock Y? Because it seems that, if we just, for instance, care about expected return and standard deviation only, that is, have mean variance preferences, it seems that X dominates Y, right? So what's the advantage of having stock Y around? Well, if you have been kind of following our discussion, we would notice that actually even though X dominates Y, the combination of X and Y may actually be still better than X, right? The reason is that we might still have stock Y actually providing diversification benefits, right? So for instance, having a portfolio which involves both X and Y might actually provide a lower risk in terms of a lower standard deviation compared to just having X, right? So let us see if we can come up with such a portfolio. So let's look at the first question. So what's the expected return of a portfolio that invests 60% in X and 40% in Y? So notice that we have all the information that is here. So we know that the expected return of a portfolio is a weighted average of the expected returns of the individual assets, and the weights are given by the weights of the different asset in the portfolio, right? So here, weight of asset X in portfolio is 60% or 0.6, and weight of asset Y in the portfolio is 40% or 0.4. So we just need to then look up what is the expected return of X, which is 20%, expected return of Y is 15%. And so therefore, the answer is the expected return of the portfolio is 0.6 into 20%. So this 0.6 is the weight of stock X in the portfolio. 20% is the expected return of stock X plus 0.4. This is the weight of stock Y in the portfolio multiplied by 15%, which is the expected return of Y in the portfolio, right? So then in that case, if we add up all these numbers, we end up getting that the expected return of the portfolio is 18%. The next question asks, what is the standard deviation of a portfolio that invests 60% in X and 40% in Y? Now, if we recall that we have covered in our lectures, that there is a standard formula for calculating the standard deviation, right? So remember that the variance of a portfolio is given by this expression that you see, summation Wi Wj times sigma ij, where you take the summation over I and j running from 1 to n. So that was the formula for the variance. So the formula for the standard deviation is that you take the square root of that, right? Now, if we apply the formula here, we have got the weights, so 60% and 40%. What are the other things that we require? So that will be Wx and Wy. The other things that we would require are sigma xx. So that is the variance, right? So we are given the standard deviation is 20%. So the variance will be the square of this. We'll also require sigma yy, which is again the variance of y. So that would be 25%. And again, you need to square it. And finally, we would require sigma xy, right? So sigma xy here, you have to work a bit because you are given sigma x, you are given sigma y, and you are given, notice the correlation, right? And not the covariance. So you need to convert this correlation into information about covariance. And the way you do it is that you remember that correlation is equal to covariance divided by the standard deviations, product of the standard deviations. And so therefore the covariance is equal to the correlation multiplied by 20% into 25%, right? So you should convert everything to decimal, by the way, to be consistent. That is a common mistake that is made, that people is think that's 20%, so that is equal to 20. That's not the case, right? So 20% is 20 by 100. So that's 0.2, right? So make sure that these two common errors are not made. So one common error being putting the information for correlation indirectly in place of covariance. So correlation and covariance are not the same thing. The variance formula that we stated involves covariance. So you need to convert this information of correlation and standard deviations into covariance, right? And the second thing that is commonly made is that just ignoring this percentage sign and thinking that 20% means equal to 20, right? So 20% is not 20, 20% is 20 by 100. So you need to accordingly place the numbers appropriately, right? So even though this seems straightforward, still there are plenty of places to make errors. Okay, so once you have put in this information, you should end up getting that the standard deviation of the portfolio is going to be approximately 17.1%. Okay, so let us note that if we have this portfolio of 60% in X and 40% in Y, the standard deviation is 17.1%. And we can compare with the standard deviation of X and Y, and we notice that this is actually less than even than the standard deviation of stock X, right? So recall that our first question was that you have got stock X already having a lower standard deviation compared to stock Y. What is the advantage of having stock Y around? But now we can see that we can actually have come up with a portfolio where if you compare the numbers, you end up with even lower standard deviation compared to the two constituent portfolios, right? So that's something very important to keep in mind, that it is not the case that the standard deviation of the portfolio will be some number which will lie between 20% and 25%. It can be some number below 20% as well, right? So that's important thing to keep in mind. Okay. All right. So the next question is about suppose that we change the correlation, right, from 0.2 to 0.6 between X and Y. What happens to the expected return and the standard deviation of the same portfolio, which has a weightage of 60% on stock X and 40% on stock Y? So here, if you notice the formula for the expected return that we had calculated, we didn't use the information about correlation in any place, right? So if the correlation changes, that's not going to be affecting our expected return of the portfolio, right? So it will still continue to be the same as that we had done. So the answer is still the same, right? That the expected return of the portfolio is not going to change if you have got that the correlation changing, right? However, if the correlation changes, we will have the standard deviation changing, right? And the reason is simple. So if you go back to this formula, we have here one part which is sigma xy, right? So if you are doing sigma xy, so that is again correlation times sigma x times sigma y. And if the correlation changes, that's the part where the formula will actually change, right? And we then will have to just recalculate that formula with a change value of correlation. And we end up seeing that the standard deviation actually ends up increasing to approximately 19.7%. So again, it's about just correctly inputting the numbers carefully, making sure to avoid these common errors that we talked about. And the second thing to note is that as the stocks are becoming more positively correlated here, we see that at least in this example, the risk, if you think about it, as measured by standard deviation, that is going up, right? Okay, so now suppose that you have been asked by a client to construct a portfolio with an expected return of 19.5%, right? What weight would you put on stocks X and Y? Now, if you think about this question, this is a bit different from the one that we have just answered in parts B, C, and D, right? In parts B, C, and D, we were actually told what's the composition of the portfolio, right? And then we calculated what's the expected return and what's the variance or the standard deviation of the return. Here, instead, what we are doing is that we are starting out with a target portfolio, right? And we are actually then constructing a portfolio which is going to have that expected return. And on the basis of that, uh, we will come up with the composition, and then we can, for instance, calculate the variance, right? So how do we come up with a portfolio which has expected return of 19.5%? So if you notice here, we have got that the stocks expected returns are given to us, right? And the key thing to remember is that the expected return is actually a weighted average of the portfolio, is a weighted average of the expected return of these stocks, right? Where the weights are basically given by the amounts that you have invested in the different stocks. So therefore, what we can do here is actually think about, suppose I decide to put a weightage of WX on stock X, and therefore the weight on stock Y has to be 1 minus WX, right? So then the expected return of the portfolio with a weight of WX on stock X is going to be WX into 20% plus 1 minus WX into 15%, right? And we want this to add up to 19.5%. So again, if we do the calculations, we'll end up getting that WX is going to be equal to 90%, and WY therefore is going to be 10% or 0.1, right? So that's how we can calculate it. The final question asks us to calculate the standard deviation of the portfolio we have constructed here. So that by now is hopefully straightforward, right? So the only thing to remember is that when you're calculating the variance formulas, remember that the weights have changed now, right? So we'll again use our usual formula for variance and then take the square root. And if you do your calculations, then the standard deviation is approximately equal to 18.7%. So hopefully this is a pretty straightforward type of a problem, but just be careful of not making some of the very kind of common type of mistakes that are made here. And that's all you need to do here. Okay, let's look at our second question. So we have got two stocks, A and B, that are available. The expected rates of return on the two stocks are R bar A and R bar B, and the variance of the returns are sigma square A and sigma square B, and the covariance of the return is given by sigma AP. So we are asked to find weights WA and WB that define a portfolio of A and B, which minimizes the total variance of the rate of return of the resulting portfolio. And after we have found that portfolio, we are also asked to calculate what is the expected return of this portfolio. So these are basically our choice variables. These are our parameters. And on the basis of this, we are asked to do this optimization problem. So how would we go about doing it? Well, let's just first write down the problem mathematically. So we are asked to minimize variance. So what is the formula for variance? So that's W square A. So this is the weight of A squared times sigma square A plus W square B plus multiplied by sigma square B. So this is again the weight of B squared up and multiplied by the variance of B plus 2 times WAWB sigma AB, right? So this is the formula for variance that we have now looked at multiple times. And we have to choose WA and WB to minimize this. And our constraint is that this is a portfolio. So therefore, WA and WB needs to add up to 1. Right? That's all there is. So how would we do it? Well, can actually do it in actually two different ways, right? So one way is that we can substitute out WB into this expression as WB equal to 1 minus WA and carry out the calculations, right? Choose WA to minimize that. So that's one way of doing it. But let us actually solve it by the Lagrangian method so as to give you a bit more practice with this method in case you are not that comfortable using it. So we have got the first step in the Lagrangian is to write down the Lagrangian, right? So how do we do that? So then first step is to write down the objective function. So this is the Lagrangian. The objective function is as we have here. So we just write that down. And the second step is to incorporate the constraints. So for instance, here we will do minus lambda times WA plus WB minus 1, right? So this is a standard way of incorporating the constraints, right? Once we have the Lagrangian, we need to look at the first order conditions. And the first order conditions would involve taking the derivative with respect to WA, WB, and lambda, and setting each of them equal to 0, right? So if we take the derivative first with respect to WA, let's see how these terms would look like. So we are going to have from this term 2 times WA sigma square A. There's no WA here. And from here, we are going to get plus 2 times WB sigma AB. And from here, we are just going to get minus lambda, right? By the way, that's another reason why in when we discuss this problem in the lecture, because of these different 2's that come up here, okay? That is a reason why we have actually this thing that you have seen, right, where we had put a half in front of it. That would not make a difference, because you recall that if you're minimizing a function, let's say fx, subject to some constraints, that's the same as minimizing some constant a times fx in front of the constraint, right? So those things would not make any difference whether you are doing the minimizing fx or minimizing some constant times fx, as long as that constant is positive, right? And half is a constant which is positive. So that's why we had those halves, so that you didn't have to worry about these 2's in the problem. But here we are going to have it. By the way, there are a couple of typos here. This should not be equal to 1, but it should actually, if you notice here, it should be equal to 0, and it should also be equal to 0, right? Fortunately, they are not going to make any error, errors in the subsequent calculations, but they should be replaced by equal to 0, and they should also be replaced by equal to 0. How do we get the second condition? So again, we are going to differentiate with respect to WB. So we have got 2 WB sigma square B. That's the first term here, plus 2 WA sigma AB. That's the second term here, minus lambda. And again, this is going to be equal to 0. So that's one way of doing it. The other way of noting is that, this is a symmetric problem, right? We could have just looked at this and just written down what would be the corresponding first order conditions for the second one. So just replace the A's with the B, right? So this, for instance, is WB. This becomes sigma B. This becomes WA, and this is sigma BA, but sigma B and sigma AB are the same because this is covariance, right? Okay. So these are the 2 conditions. So these are again both equal to 0. And the third one, if you differentiate with respect to lambda, you end up getting that WA plus WB minus 1 is equal to 0. And so therefore WA plus WB equal to 1. So how do we go about solving it? Well, we'll note that if you write this first 2 equations in terms of lambda, you end up getting that this expression is equal to lambda, and this expression is also equal to lambda, right? So we can actually equate these 2 terms. And if we do that, and then cancel the 2's from this equation, and finally, we can then replace out WB with 1 minus WA. So we end up getting one equation in one unknown WA, right? And if you now solve for this WA, you can see that this ends up being equal to sigma square B minus sigma AB divided by sigma square A plus sigma square B minus 2 sigma AB. Okay. So that's how you can do the calculation. And finally, WB is just 1 minus WA. So you can also do the calculation for WB, right? The other thing to notice is that, again, one check that you can have at the end is that here the problem is symmetric in terms of A and B. So whatever WA that you had got, if you just replace the B's with A's, you should actually end up getting the WB, right? But use this as a check rather than just coming up with the answer, because another common mistake is sometimes we apply symmetry when we shouldn't apply it. So we should be careful in applying it. And the second part asked us to calculate the expected rate of return of this portfolio. So we have already calculated the weights, and we had information about the expected rate of return of the individual stocks. So we can just write down what is the expected rate of return, right? So you will have to just put in this information here, and you will end up getting the answer. Okay, let's look at a third question, and this is related to flood insurance, but now in the context of portfolio optimization, right? So you've got Ravideep, who is planning to invest 1 million units of money in a farm next to the river. He believes that this investment can actually be converted to 3 million revenue from the farm next year if the river does not flood. However, if the river floods, then all the produce in the farm is going to be damaged, and therefore he will lose the entire investment, right? Because he'll not be able to make any money from this, right? So this is a common occurrence potentially if you are next to a river, because the land may be potentially be fertile, but if you have flooding, then that may actually lead to a lot of damages, right? So there's a 50% chance it will flood, and Ravideep can also buy insurance. So for each unit coverage of insurance that he is buying, he has to pay 0.50, and each unit of coverage basically is such that it pays 1 to him if the river floods and 0 otherwise, right? So he can decide how many units he wants to purchase, and the maximum amount of insurance he can purchase is 3 million units. Okay, so this is the setup that we have, and we have to answer the following questions on the basis of this information. So the first question is, what is the expected rate of return on this investment if Ravideep buys 0 units of, U units of insurance? And the second question is, what are the number of units that will minimize the variance of his return? What is this minimum value, and what is the corresponding expected rate of return? So here, the important thing is to kind of think about the problem a bit before just starting to write down, okay, thinking about this as a portfolio, and then writing down the expression for the variance of the portfolio in terms of the constituent assets and so on, right? So, often we are kind of inclined to always start down by writing down the variance formulas and then doing the optimization exercises that we have here. But sometimes it's worth actually thinking about the problem a bit more and then going ahead and doing the calculations, right? But first, before we get to the second part, let's first actually look at the expected rate of return on this investment. So Ravideep has bought U units of insurance. So how do we calculate the expected rate of return? Well, we can calculate it as the expected total return minus 1, right? Remember that we had this relationship between the rate of return and total return. So which was the rate of return is equal to total return minus 1. So expectation of the rate of return is expected total return minus 1. So what's the expected total return? So if he buys U units of insurance, so what is the total amount of money that he has invested in this farm plus insurance? So remember, he had to invest 1 million in the farm, and then he has spent money on buying U units. So each unit costs 0.50. So U units cost 0.50 into U. So therefore, this is the total amount of money that he has put in, right? And how much is this amount of money going to become next time? So this is the expected payoff, right, that we have to calculate. So with probability 0.5, there is no flood, right? In this case, this 1 million will become 3 million revenue, right? And there is not going to be any payout with the insurance company, right? So therefore, in the event that there is no flood, he is going to have a payout of 3 million, right? Which is the revenue that he gets. And we need to multiply this with the probability that this event will happen, which is 50%. Now, there's a 50% chance that it will flood, in which case he's not going to get any revenue from the farm, but here the insurance is going to kick in and he's going to get a payout from the insurance company, right? So if he has purchased U units of insurance, then the insurance company is going to pay him out U units of money, right? So therefore, his total payout, if there is a flood, is equal to U. And therefore, this again happens with probability 50%. So we need to multiply by 0.5. So what you see in the numerator is the expected payout, right? So that's equal to 50% times 3 million plus 50% times U. And in the denominator, you have the initial investment. So that's 1 million plus 0.5 U, right? So notice that the two 0.5s that we have here, these are due to different reasons, right? You have this 0.5 here because that's the probability of payout of U, and you have 0.5 here because that's the cost of purchasing U, right? And finally, we need to subtract the 1 because we are asked to calculate the expected rate of return and not the expected total return. Okay, so that's the first expression. Now, the second expression, without even writing down the formula of the variance of the portfolio and so on, you can think about it. So recall that basically what we are doing here is that we have an opportunity of eliminating all risks, right? How do we do that? Because remember, there is a risk that he does not get the 3 million, in fact, gets 0. But if he actually ends up purchasing insurance worth 3 million, this will actually end up eliminating all risk, right? Because then in that case, his payout in both cases is going to be 3 million, right? And therefore, this is one way of doing it. And in fact, this is the lowest variance that he can have, right? So if he buys 3 million units, that would lead to elimination of all uncertainty. And hence, variance would be equal to 0 in this case, right? Remember, we were asked to calculate the number of units which will minimize the variance of this return, right? What is this minimum value? So the minimum variance that you can achieve here is equal to 0. And what's the corresponding expected rate of return? Well, you need to buy U equal to 3 million in order to actually achieve this 0 variance outcome. And so therefore, if we put in that information here, we end up getting 1 million plus half of 3 million. So that's 2.5 million. And here we have got 3 million, right? So this expected rate of return actually simplifies to 3 divided by 2.5. So it's like 3 million in by 2.5 million. So the millions basically cancel out. So you end up getting 3 by 2.5 and minus 1, right? So therefore, this is equal to 0.5 by 2.5 or 20%. So that's the final answer here. Okay, so let's look at the final practice problem. So suppose that we have got n assets which are uncorrelated, and we can invest in any one of these assets or any combination of these assets in the way that we have discussed in the lectures. We are given the information that these assets have such that the mean rate of return is the same for each of them. So that's all equal to R bar. However, the variances are all different, right? So we can actually rank the assets as per the variance. The variance of asset I is given by sigma square I, right? So again, just to summarize, we are given information about the mean. So each of the assets have the rate of return, mean rate of return being R bar. The variances of the rate of return are sigma square I, and we are also told that the assets are uncorrelated. So on the basis of this, we are asked to answer the following questions: that how would we actually think about plotting this in the standard expected return standard deviation diagram that we have? And after that, we are also asked to calculate what's the global minimum variance portfolio. So the first thing to note is that given that the expected return of the assets are all the same, so they are all going to be lying on the same horizontal line, right? Which is going to correspond to the expected return equal to this R bar, right? So if we line them up, these are all going to be dots on the same line, right? And the only other thing to notice is that the efficient set is going to just be a single point here, right? And it's actually, we'll see, going to lie to the left of the leftmost of this n original points corresponding to each of the assets, right? So let's now calculate what is going to be the combination that gives us the most uh, minimum variance. So we have got that, suppose that Wi is the weight of asset I. So then if you want to minimize the variance, remember this is what we are asked to calculate, then in that case, here the expression for the variance is pretty simple. It's just summation over I Wi square sigma I square, right? Why is this term so much simpler than the usual ones? Because remember that these assets are uncorrelated. So all the cross terms basically dropped out, right? So you ended up just having this n terms, which is W1 square sigma 1 square plus W2 square sigma 2 square, so on, right? And we still have the constraint that these are subject to summation over I Wi equal to 1, right? Because this is a portfolio after all. Okay, how do we solve this? We now know how to proceed. We will first actually set up the Lagrangian. So again, this is first writing down the objective function. This is this term. And then again, incorporating the constraints in the standard way. So this is the Lagrangian. What are the choice variables? So here we have the n weights that we have to choose. And the other thing that we will need to take the derivative with respect to is lambda, which is the Lagrange multiplier. So we have got n plus 1 partial derivatives to take, and we are going to be equating all of these partial derivatives to 0, right? So if we go ahead and do those calculations, then we get that del Wi is equal to 0. So here the only place where Wi is going to come is in one term, right? So for example, suppose we are taking the derivative with respect to W1. So the only place where W1 is going to come is W1 square sigma square 1, right? And it will not come in any other terms. So therefore, you end up getting 2 Wi sigma square I. And from here, we get minus lambda. That's equal to 0, right? So that's the condition for I, and you are going to have n such conditions. And finally, if you take the derivative with respect to lambda and set it equal to 0, you end up getting that summation over I Wi is equal to 1. So n plus 1 equations in n plus 1 unknowns. How do we go about solving it? Well, we can actually think about rewriting first this Wi in terms of lambda. So you end up getting that Wi is equal to lambda by 2 sigma square I. And remember that this sigma square i's are actually parameters to us, right? So then we can actually put this in the second equation. So we end up getting that summation over I lambda by 2 sigma square I is equal to 1. And we can solve for lambda in terms of the parameters. Once we have solved for lambda, we can put that lambda value back in, and then we'll end up with an expression where we have got lambda in terms of the parameters. So on the right hand side, we'll have all parameters, and here we'll have 2 Wi sigma I squared. So again, we can solve for the Wi's, and if you go ahead and do those calculation, you will find that this is the value of the Wi that you get, right? So this is notice in terms of the parameters of the problem, the sigma squares i's. Okay. So now we were asked to figure out what's the minimum variance, right? So the minimum variance here, if you go ahead and do the calculation, so we need to square this term, right? Remember, this is the minimum variance that we had. So you need to square this term. And then if you go ahead and do the algebra, it's a bit tricky, but it's not that complicated. You can show that this is actually the final expression that you end up with. Okay, so that's the final answers for the minimum variance, and these are some practice problems that we had. Okay, so the two references, so one is this classic book on investment called Investment Science by David Leuenberger. So that's published by Oxford University Press. You can use either of the editions. And the second resource that we had, and this is something that we used a lot to kind of come up with the figures that you see, is this interactive website. It's called Learn Investments, and it's developed by two professors who are at Rice Business School. And this is available online, right? So the nice thing about this website is that not only can you get these nice figures, but you can also play around with the sliders, right? And you can also get to see visually how different things look like as you change the parameters. Okay. And the other thing that is useful is that they also provide codes in Python for implementing this some of these things about portfolio optimization that we have seen. So I encourage you to kind of go to that website and check it out, especially the ones corresponding to the portfolio optimization that we have seen. And we'll come back and actually look at some more aspects of this portfolio theory next time that we meet.